it scales terribly computatively. Think about computing an arithmetic mean value of a large list of numbers. Maybe the list of numbers is so large that it doesn't fit into your memory of the computer. Then that is not a problem, because it's just taking a sum of these data. So you can split up your large list of numbers in small chunks, add them up for each chunk, and then add up all the chunks. And then compute, well, divided by the number of data points, and you are done. No matter how big your memory is, as long as it fits at least 2 of the numbers, it's okay. You can do this. Now think of how the median is computed. You take all your data, then you resort it. Yeah, it has to be in the memory, because if I add an additional data point, I need to look where it fits. Yeah? And only after I have the whole data in the memory, I can determine the median point. Okay? Okay. Yet now, computers have huge memories nowadays. Yeah, we are talking about gigabyte. But still, think about a common application in astronomy, for example, in pulsar physics, is that you have radio telescopes observing patches of the sky, but not for a very long time, but for a short time. And since pulsars are very distant sources, they are not very bright. Yeah? So it's taking a photo of a very, very low brightness thing. And usually the noise that your detector generates is much higher than the signal of the detector. So one way to help yourself is, of course, is to reduce the noise. And in astronomy, what you usually do is you try to observe longer. I don't know the English word for Belichtungszeit. What's Yoko, do you know? It's basically integration time. You try to integrate more photons from the source and make use of the fact that the noise that you observe is random, uncorrelated and random. That means for a single point in my image, on the first picture it has a random number, on the second picture it has a random number, and so on and so on. And if I add them up, they start to cancel out because they are uncorrelated. Yeah? The average value is 0. So that means if I have many of these images of the same portion of the sky, I can add them up to reduce the noise until the signal is stronger than the noise. So every astronomer does this in one way or the other. Now imagine that we would like to have a robust adding up of the images. We don't want to use the average value, we want to use a median image. Yeah? So that means we have to take one image. So let's take a look at the scaling. Oops. Scaling. Let's say we have an image of size 200 times 200 pixel. A small image, but common size for astronomical data. So that means we have 40,000 pixel. One pixel, every pixel, of course, is a number. Some intensity, some number of photons, basically, in a way. And let's say that they are stored in double precision computer accuracy. So that means every pixel takes 8 bytes in our computer memory. So that means one image takes up 40,000 times 8 bytes. So what's 8 by 4, that's 32 times 10 to the 4 bytes. 320 kilobytes. Okay? And in pulsar observations, you usually have 10,000 or 100,000 of images, short exposure images of the same sky. Only parts of a second exposure time. Let's say we have 100. Let's say we have 10,000 images. So that means what we have is 32 times 10 to the 4 times 10 to the 4 bytes. Yeah, this is this 10 to the 4, and here that's this. So 3.2 times 10 to the 9 byte or gigabyte. That's already sufficient for most of the PC computers that you have. Maybe you have 8 gigabyte memory, but that's usually the limit. But that's only 10,000 images. If we have 100,000, it's already 32 gigabyte. If we have 600,000, we are in the hundreds of gigabyte. Memory that we need to compute one median image. Okay, so that's a problem.